In our continuing series on distributed systems engineering, I talked to my colleague Adithya Chandra about performance optimization in distributed systems. There are some really neat things that he's gotten into, and he shares them with us on today's episode of Streaming Audio, a podcast about Kafka, Confluent, and the cloud. Hello and welcome to another episode of Streaming Audio. I am, as always, your host, Tim Berglund, and I'm joined in the virtual studio today, which is a virtual video studio also. Just as a reminder, these are available on YouTube as well as in audio format. Anyway, I'm joined in the virtual studio today by my coworker, Adithya Chandra. Adithya, welcome to Streaming Audio.
Yeah, thanks, Tim. Thanks for inviting me, and it's great to be on the show and talk about distributed systems.
Cool. Now, you are an engineer in the Kafka Performance team here at Confluent, and this is one of our episodes in a series where we're talking about distributed systems engineering. So I want to talk a little bit about what you actually do on the Kafka Performance team, but also about how you got into that kind of work and just what separates it from other kinds of engineering.
Yeah, that sounds great. And in the Kafka Performance team, we are looking mostly at improving Kafka performance in terms of scalability, in terms of cost. Uh, and a big chunk of it is like running Kafka super efficiently on Confluent Cloud, so that we get the biggest bang for the buck when we are running it there. And also, scalability in terms of we have lots of customers, and all of them have completely different use cases. How do we run Kafka efficiently for each one of them? And especially there are these use cases with, there'll be some customers who are really large, some customers who are really small, some customers who have large message sizes, some of them have small message sizes. It's a whole bunch of things. And so we will really want to focus on that to improve it, and uh, uh, like have a platform where you like our customers don't have to worry about performance at all. They can throw any kind of workload, and we should be able to handle it. So that's kind of what excites me about working on this. And how I got here, basically, I've been working. I was at AWS for 7 years before this, pretty long time working on the cloud as it grew. There was tremendous growth, and I worked on Aurora on the storage layer where I did I did like cluster management, load balancing, etc. And I
Could you
also
remind
worked.
us what AWS Aurora is?
So yeah, AWS Aurora is this. Uh, it's a MySQL and Postgres compatible database, but the key innovation was this separate storage layer. The incredible thing was, if you have these block storage layers where you're writing, if you have Elastic Block Storage (EBS) in AWS, where you're writing, like, say, 512K blocks to the disk, like 512 bytes. But in like what you can do in the Aurora storage engine, instead of entire blocks, you can write diffs. It can be small diffs, it can be a small number of bytes, it can be large number of bytes. So for a storage engine that is on on the network, it's kind of like the Kafka, like using Kafka, right? It's something on the network. If you just write the changes instead of writing an entire page each time, I mean, like large number of blocks, which is a collection of pages, what you get is the amount of, if network is your bottleneck, the amount of stuff you have to write on the network goes down significantly. So then on our storage side, what we would do is, depending on the database that you have, we could apply those changes, and then we could support a ton of features because of that key change. So that was a really interesting innovation that was done at AWS. And the storage engine had like tons of features because of that. We would like a typical thing that happens in a database is, when you like go down and then you have to recover, you have to replay all these changes. So if you have a normal MySQL, all the changes get replayed on a single instance. But in this case, what happens is you have all these, you have this big storage cluster, When you're not writing to a single storage instance, instead of your database is now writing to, let's say, 100 or 20, 50, depends on how big our storage clusters. So let's say 100, and all of these can replay the changes because they've got a subset of these changes, and they can come back, and they're almost like, so when your database restarts, it's catching up really quickly. You can just say, hey, give me the latest version of the page, and they would like replay it and give you the latest version. So that was amazing. So the restart times were fast, and we could do availability, right. Instead of you having to worry, we would have these instances in different AZs, so you wouldn't lose data if any one of them went through. So it was much highly available, and we could also do backup online, where again your main instance doesn't have to worry about backup. You have these other these storage servers which are collecting all these changes logs, and they're like actually working through them and then persisting them on disk, but they're also like have these backup things which are pulling this and persisting it, let's say in S3 or like something that is cheaper storage. So you get that, like you get online backups which are always up to date. Like, you don't have to worry about it. So these were some of the features, and then there were a bunch of other things that got built on top of it. Like you could clone your storage volumes pretty quickly, because now it's on the cloud. I mean, not on, like you have these storage clusters basically, and then if you spin up a new database cluster which needs to a new database instance from your current one, which needs to point to this, then you can just have it can be the same storage nodes that it talks to. It just needs to decide from what point you would have cloned, and then only writes from there would be written separately. So that was an interesting feature. And you also have becomes very interesting in terms of replicas. Like you have all these replicas sitting around in your database. Your master is writing, and the replicas can now separately read from the storage. So it's kind of like separating storage compute, and it gives you all these advantages because you have these replicas that can directly read from these storage clusters. They can ask, hey, give me this page or that page, whichever page they're interested in, and they can decide how much they'll cache. They don't have to cache everything from the master. They still have to do for transactions, etc. There are a bunch of nuances to this, but this is the high level thing of how it was beneficial. And
And it
yeah,
sounds
so
like
that was
7 years. Oh, go ahead.
so that was just one part of it. After that, I wanted to talk about performance, but that's another story. So uh,
Yeah,
yeah, I mean, in
but it
terms
sounds like
of
that's good preparation. 7 years of that was good training for more distributed systems work, right? You spent
yes,
a lot of
so
time
the
building
key,
really a pretty interesting product. That sounds like there's some sort of log like concepts in there that enabled some of that coolness, if I heard you
yes,
right.
definitely, yes,
Um,
definitely. It was
yeah,
basically a log.
it's
So you
amazing what
write,
happens when you use logs.
yes, yes, definitely, yeah.
Um, cool. So
So
you
yeah, I
came
mean, there
from
was a
there
bit more.
into Kafka performance engineering.
Right. So there was a segue after that. So yeah, I mean, I went off talking about Aurora for a long time, but the other thing that I did was I was also part of the Elasticsearch team at AWS,
Ah,
and a key problem there was a slightly different problem. Was like we had all these instances, clusters of Elasticsearch running, and managing it was pretty significant problem because there were just so many of these, and to do a really good job of managing it, you had to understand the performance and what is actually happening in each of them. So we built something called performance analyzer that looked at like where for each particular cluster, where is your CPU, where are your resources being used, like who's using your CPU, who's using where is memory being allocated, who are the top consumers, so that we could then take decisions on better load balancing and better auto tuning. So recently, Amazon launched Amazon Auto Tune, in their Elasticsearch service, which utilizes a lot of these things to automatically tune things like how much memory to allocate, where to allocate memory, and yeah, I mean, and go, like you can use that for a lot of things that we do on Kafka as well. Like you can call it, like we have
Yeah.
these self-balancing clusters which can automatically move stuff around and load balance. So that's kind of how I ended up in this team.
That's their auto tune, not to be confused with the voice processing auto tune service. Completely different thing, right?
Yeah,
Um, yeah, that some of us, when we sing, we could use that. Um, so yeah, tell us about how then you came into the Kafka performance team, because I always like to know, uh, when I talk to people who do the kind of work that you do, how did you get there? And it seems like, I don't know, 7 years building Aurora and Elasticsearch Autotune things would be pretty good preparation. But tell us a little bit about what you do now.
sure. Yeah, so now I think the first project I looked at was like how can we improve costs at Confluent Cloud? How can we actually take Kafka and run it with like half the memory? So that was very interesting to
Hmm.
me. Like having worked at Aurora, which was logs, but the abstraction for the user was not logs, and Kafka just takes logs and the abstraction is logs. So I think that's super powerful. So a lot of the things that we built on the storage engine was actually logs, right? Like how do we take this? Where's the incoming queue? Like how do you persist it on disk? A lot of it was that. And if you can, move some parts of it, and anybody can consume the log. Like I could clearly tell that, this is super powerful, and it enables you to build a lot of interesting software on top of it. Like Aurora, you can have all these databases that use this. Uh, so I was overall interested in this, and at Confluent, so the first thing I worked on was this, like basically run it with half the memory. And the interesting thing there was like I spent a bunch of time in Elasticsearch where memory was a big problem. So you had to understand where is memory actually being allocated. But in Kafka, it's like Kafka is super good at memory, right? It uses like I was surprised that it uses such a small amount of memory. It's a storage system, and we were like it runs with like 6 GB of the JVM heap. So for
Mhm.
context, heap is where we allocate most of the objects in Java. When you create a new object, it's allocated on the heap, and the references to it are held in the stack. And and so you need a larger heap if you have a lot of these live objects that you are constantly
Mhm.
like using. And Kafka, because it persists things to the disk, and it also uses the operating system page cache for more efficient IO, doesn't really keep too much of these live objects at any point in time. The working set is pretty small. So that was interesting. Like I got an opportunity to look at all the production clusters in Confluent that are running, generate a lot of synthetic workloads to understand for different use cases where you have high and different message sizes. Where you have consumers lagging, consumers who are consuming immediately after a producer, etc. And yeah, I mean, we were able to. So Kafka runs really well with even just 6 GB of heap, but what we saw is for a lot of cases, you don't even need 6 GB. You can go to like 4 GB and still get fantastic performance. I mean, that's pretty small. And the working set size was like a gigabyte of memory. Like the allocation rate was also not so high that we needed too much more. And that was interesting. So there was a bunch of things around how do you measure this? What do we do when if there are certain cases where where you exceed this total heap utilization? Uh, so those are some of the interesting problems. And the other interesting thing was the page cache itself, which is used to
Yeah.
improve IO reads and IO writes. And also, like I forgot to mention, to set the context, was this possible? Right? Why? How can you, out of the blue, shrink memory by 50%? Why was it not possible before? I think the key thing was we started using much better disks. And how did we start using much better disks? Like the thing to keep in mind is we have all these SSDs now, which are super
Yes.
good in terms of bandwidth. So they're very fast. You can do random reads, etc. But they're very expensive in terms of per gigabyte cost. Like if you now have, like, say, 10 gigabyte, like if you have a terabyte of an SSD, it's pretty expensive. But Confluent launched a tiered storage, which allows us to move all this data, which is slightly older, to a different tier, a cheaper tier, which where the cost per gigabyte is much smaller, but bandwidth is a lot more expensive, slower, so throughput can suffer. So what we did is we moved to SSDs for the tier immediately to what is attached to the broker, and there we got much higher bandwidth. So what happens when you shrink your page cache is that your writes can get smaller, your reads can get a little more frequent, but this SSD can do bandwidth really well. It's more expensive if you want to provision a lot. We don't need to provision a lot anymore because we have uh, infinite storage where we go to S3, or we go to a different object storage in the cloud. And so that was what that really enabled us, and we were able to shrink the page cache significantly. We had to tune parts of it. We've found interesting tuning lessons as part of this exercise. So there are two main things that you need to understand about the page cache. Basic thing is when Kafka writes to the disk. When so you have, let's say you have a file per partition in Kafka, and you wrote all these records to it, and these records are not immediately written to the disk, because let's say you have a lot of partitions. Let's say you have 1,000 partitions, you have 1,000 files, and they're all small updates that are going to each file. So what Kafka does is it just tells the operating system, hey, I want to write all these things, and all these things are kept in memory and not immediately flushed to the disk. And then we have these configs where we tell, where the operating system has these flusher threads that wake up every once in a while, depending on your config, and then write all these to disk. But when they're writing it,
And
the
these are
thing that they
operating
can,
system level flusher threads. This is not in
yes,
Kafka,
these,
right?
yeah, these are operating system level flusher threads. And the thing that you can do here, the operating system does, the drivers, like for example, if we take EBS, which is the AWS equivalent, what it can do is it can take 32K sequential reads. Let's say you have multiple updates that are next to each other. It can combine them into a single 256K write. I can write it in one write, and that is a lot more efficient. So you get a bit much higher bandwidth by doing this buffering, and so your disk throughput is like you can get much higher throughput with the same disk. So that's the advantage of a bigger cache. So you can keep things longer in memory. And you can also, like, the other way it works is if you're changing the same piece of information multiple times, and then we write it to disk only once. This doesn't happen very frequently with Kafka, but there are some metadata files where this can happen. So that can also reduce the amount of I/O that you want. So that's how it's efficient. And on the read side, how it's efficient is basically when you're making these changes, they're all kept in RAM. So if your consumers come up and read immediately after a producer, which is what we see in most of the use cases, the consumer lag is in milliseconds in most cases. People come up and read what's written almost instantaneously. Then you can service it directly from your memory. You don't have to go to the disk at all. You have all the things that have been written, and you've kept it in this fast but transient storage in main memory, and you just give the responses back. So this is another thing. So what happens here is if you shrink the cache, then you have lesser amount of time that you'd want to keep there. And so that was pretty interesting. And some of the things that we have advantages in the future that we should look at is uh, when do we do out of band reads? For example, one thing that comes up and does reads is the tiered archiver, where we're actually moving stuff to a different tier. And for that, we want to read in bigger batches.
Ah, right. And those are older. Those are older
That
messages by definition.
Yeah, right. And those are older
Yeah.
messages by
With apologies to the
definition. So
page cache.
So yeah, so
Yeah.
that is not going to hit. So if your goal is everything has to hit the page cache, that's not going to happen. So that's where SSDs help. So it's good for them to read. But the thing that we want to do is it should probably directly read from the disk. It doesn't have to come to the cache. Because once it writes to S3, the other optimization we have is once it's written to an object store, if you read something from the object store, we service it directly. It doesn't go to the cache anymore because we think this is historical data and then it may not be read again. So we can directly
Mhm.
send it to the consumers that are requesting it. So that way it does not pollute the cache for all these new writes and new reads that are happening inside the uh, so that is one. And yeah, I mean, in terms of improvements, what we can do is when it starts moving, we can skip the cache. Another thing to keep in mind, this was a very interesting, is how the page cache itself works, right? Like when those flusher threads come up and write to this. So one thing we tried is we actually configured those flusher threads to come in very late so that you'll have as much, like say you have a lot of writes that are in memory, and then they come up very late and they write. And then we noticed this interesting thing. We actually got more writes, more smaller writes, with a large flusher thread. I mean, large if they came up much later versus something that came up earlier. And this was very hard to understand, so we had to look at a bunch of traces, etc., from the operating system. Yeah, but from what we understand, what is happening here is that if you wait too long, there are all these other consumers. So you have to understand how the read cache bit of the page cache works. It's basically a LRU cache, so least recently used. So whoever is
Okay.
reading, they go to the top of the cache. So anything that was updated slightly old starts going to the end of it, and you have a fixed amount of space. So when you run out of space, everything at the end gets thrown away. And in case it's not
Right.
written, if it's a write buffer, then it gets written to disk. So now what happens is if you delay the flusher threads long enough, then the actual memory pressure kicks in, it goes to the end of the LRU and gets written to disk. So you get again small writes that can actually get written. So the main advantage we got with the flusher threads was they would come up and write in these batches where they would take a bunch of guys and then put these sequential writes. Instead, if we made it large enough, then these writes would reach the end of the LRU and then instead get written like in that process. That was also interesting. So you
Do you
want
still get a
to
big do you still get a big gain on SSDs doing larger sequential writes? Does that matter as much?
no, like it's not much larger sequential writes. For example, like on EBS, like the max for a hard disk is a megabyte in terms of writes. For an SSD, it's just 256K. But with 256K, you do get a benefit in terms of it doesn't have to be. And another thing to keep in mind is that this is not just SSD, right? You also have these cloud provider things where it's going over the network. So there are other things in between where a bigger batch does help. So uh, so yeah, to your
Gotcha.
point, it's still faster in terms of 4K, and I think it's not just probably sequential, but in this case, like it's a single call, and yeah, so that's what we've seen from our experiments that we could actually bring it down by like a factor of 2 or 3 by tuning this buffer size well.
Oh wow.
But they're very
Nice.
fast. So yeah, I mean the final thing is
Now,
these SSDs are so fast that it actually doesn't matter. From what you said, like what you were saying, in most cases it doesn't matter unless you have particular use cases where you have thousands of partitions, you have thousands, they're all writing different places, they're small, but it's still pretty hard to exhaust IOPS on some of these modern ones.
now, to some degree, performance optimization is everybody's problem, right? Whether you work in distributed systems or not, you're gonna at some point you're gonna do performance optimization. Now, we always talk about doing that prematurely and how it's sort of fun and we easily get sucked into it even before it's economically useful to do. But let's just agree that it's everyone's task. How do you think? And I mean, I've heard you say all this, so I think the answer is in the previous 10 minutes, but I wonder how you would describe the difference between performance optimization as a distributed systems engineer relative to something else. I know there's a lot of different kinds of things one can build that aren't distributed systems, but what
Hmm.
makes this different in your mind?
Yeah, that's pretty Interesting, right? Like the first thing that that changes, like you said, like you have multiple things, but let's say when we say distributed, it's something with the network, and you have two different people who are communicating with each other, and a lot of the things that we see actually comes from this particular thing. Uh, so the main thing that we've focused on is, and the thing we see over and over again is that if you batch better, you get good performance in terms of lower CPU utilization and higher throughput, but you get worse performance in terms of latency. And that is kind of
Right.
what we are always fighting against, and that's where a lot of these improvements in our team that we're working on, like we are also looking at, say, replication improvements, uh, where like if you have like, again, there's the system part, like you mentioned, like if you have 1,000 like 1,000 partitions, that kind of can be done on on another software that's working on a single like instance. But you also have 1,000 partitions, and then in Kafka, what we have is we have three replicas, and then if you have replicas, like and so that is like 3,000 replicas. And now that this particular guy, let's say you have 1,000 leaders, and then you have like 2,000 other followers that it has to that have to replicate from this. And if these are all in, say, different hosts, for example, let's say you have a 100 broker cluster, then what will happen is all the 99 will have to talk to this particular broker, and all 99 will have to replicate from this, because that's how we have spread it. And then you'll have these smaller rights, and you'll have a larger overhead, versus, like, for example, if you brought them closer, like if you had these things distributed around, let's say, just 20 brokers or 15 brokers, now only 14 of them. And if you this single broker is getting, like, say, 10 megabytes per second, then it only gets divided among them, and we're just replicating, like we're just doing IO of, like, say, a megabyte, or probably even lower, but we can get much better performance. So these are the kind of things that come up only in a distributed systems environment, because it's a question of how are you distributing, like, work across all these guys, how are they talking to each other, which parts are they and the other thing is, this is again not even like in distributed systems, right? Like, this is the like if you have 1,000 different partitions, and then two brokers are talking to each other, and then what they're looking at is, there are a bunch of changes, and then the second broker gets all the updates from the first broker, and it has to, let's say, go through each one of them. It goes in a loop, and it looks at, hey, do you have changes? Do you have changes? Do you have changes? And that starts spending CPU. And what you can do better is, if you can have a notification mechanism where this other broker knows, hey, these are the only ones. Most of the times we don't expect changes because we're constantly replicating, and these are the only partitions that have data. Then you can again do like you can be more efficient when you are exchanging or replicating. And this is another place which probably only comes up in this distributed system space. And there's also the whole load balancing question, which is very interesting. Like, how do you balance across all these guys? Do you balance for the resources are the same? Do you balance for CPU? Do you balance for memory? Do you balance for network? Do you balance? And then you have these interesting like heuristics. Basically, you can look at number of partitions, number of leaders, and just do balancing on that, so that you don't, it's a little confusing to look at all these other things. So if you just balance that, that acts as a pretty good proxy for all these other resource utilization that I spoke about. And this only comes up in distributed systems because you have these so many small ones, and you have these you have this opportunity to, like, assign work to each of them, and you get to decide over time like how things are changing. And then you have this load balancing opportunity. If it was a single instance, you wouldn't have it. And it also opens up a bunch of things around sizing. It opens up a bunch of stuff around what kind of instances should you run, right? Because we can, like, split up work in these different ways, we have the opportunity to either use small instances or large instances. And then we want to use the ones where we have a perfect performance. So if you can think about it, if you use a large instance, depending on your workload, the advantage that you get is when you have very high throughput, suddenly the number of other brokers that it needs to replicate from will be smaller because all of them are bigger. So you get this performance improvement in terms of better batching. But the big downside is now you have these large instances. When you don't have traffic, you're losing a lot of money that you're leaving on the table. They're sitting around doing nothing. And also it may be harder to get them. And then if one broker goes down, there's a bigger blast radius probably. So there's this other advantage of going with these smaller ones. And then from a performance perspective, you need to look at, hey, how small can you go? How wide can you go? And there are all these scalability bottlenecks that will start coming up in your metadata. If you go to really small instances, what happens when you go to 100 brokers? Where exactly do you hit bottlenecks? Should we go to 100 small brokers or should we go to 10 large brokers? That becomes a completely different way to look at it, which only comes up with distributed systems, because now we have the ability to easily load balance. We have the ability to move things around, and so we can start thinking about these things. And another area that comes up is like isolation, like we want to have guaranteed performance. You want your P99 latencies, etc., to not be affected. Let's say you have some clients which misbehave a little bit with some code path that doesn't have the right quotas, and suddenly like it uses a lot more memory than what is expected, and then it can fail. And when it fails, it can take down, it can affect performance for everyone else, right? So in addition to all these things, we can take decisions on how we would have distributed these in terms of your topics or tenants, however you want to look at it. And that gives you the opportunity to have fault tolerance. If you have a large cluster of 100 brokers or larger, you can say, hey, these 10 are only for this kind of workload. So if it goes down, I know these are the topics that will get affected. And I'm sure that everything else will probably keep running pretty well, even though this is kind of affected. So that's the other angle to look at. So yeah.
So we're coming up against time here. I want to ask one more question. If you had one word of advice to give to an engineer who was not currently working in distributed systems, but was listening to this and thinking, well, there's a lot of performance optimization stuff there. I kind of know that, but there's these additional aspects of like the network and things that are interesting and just it seems fun to some people, right? This is a really appealing kind of work. What would your advice be to somebody who is a software developer who isn't working in distributed systems engineering right now, but wants to be? How do you get started? Short answer.
How do you get? Yeah, I mean, like I would say, I mean, it depends on where you're starting from. I would say a good starting point is start using these systems like Apache Kafka, etc. Like install it, start using it, and also start from something very basic. Don't worry, like performance optimization probably happens a little later, but just for the to play around with, you can start different like processes, figure out how they can communicate with each other. There are standard things that you can use, like say gRPC, or you can make HTTP calls, set that up, look at how things would talk to each other. And then this basic things of how a basic thing around how things talk to each other, even if you don't go to all the levels of details around like TCP, and then where does time get spent, even just having a high level understanding, making calls with two different processes that can run at the same time, and then now it's very easy to spin up VMs and to spin up things on different computers. So then if you can actually bring these up on different computers, you'll go through all the basic things that come up over and over again, which is basically discovery. How do these two guys talk to each other? How do they know where they are? And then, like if you are interested in performance, then you can start asking, if I send a single request, how much time is it going to take? And then if I say keep the, where do I put those instances? If I put them close to each other in the same building, what kind of latency do I expect? if I put them far away, and you can do this with the cloud providers today because they allow you different AZs, different zones, different regions, and then you start saying, hey, this is what I expect, and then you get a feel for what is happening. And when you don't see that, when you don't when you say, like, that an instruction in a computer, if it's a 2 gigahertz processor, takes so much time, and then you'll start seeing patterns around, hey, this doesn't seem right. This should be taking like a millisecond, it's taking like 10, 20, 100 milliseconds. Then there must be an opportunity here. Where is time going? And I think that's a pretty good way to get started, get excited about it. And you would start from the basics, right? You would start from the fundamentals. And there isn't a lot, I mean, there's a lot of details and complexity as you start looking at it, but fundamentally it's pretty simple. Like, it's like two people talking, and you kind of understand, hey, these are the guys, this is what you must be doing. For latency, like, you should be able to process messages when that person's messages come, otherwise it's going to be slow. So yeah, I mean, building something like very basic, exchange some basic messages, then you'll develop a pretty good understanding of whether you like this field and why it's exciting, which are the parts where things can go wrong. And then there's also failures. So we do a bunch of things around things going wrong. This is the next level where you can inject issues. What happens if there's some issue with these two, you can't talk? What happens? There's suddenly a bunch of messages. What happens? There's a large message, small message. So yeah, with a very small, setup, you can start playing with all these different things to start building your intuition around what is happening and what is possible today. So you can work with hardware that is possible today, and as new hardware and new things come up, all of this will change. So then that will give you a feel for how things will change over time. As something might become faster, something might become cheaper. Like, SSDs get cheaper, memory doesn't get so cheap. So you will shrink memory and you'll pay a little more for SSDs. And that gives you a big benefit in cost. But tomorrow, memory might become cheaper or something else might change. And yeah, I think that's how it will evolve over time.
My guest today has been Adithya Chandra. Adithya, thanks for being a part of Streaming Audio.
Thanks, Tim. Thanks a lot. It was great being here with you.
And there you have it. Hey, you know what you get for listening to the end? Some free Confluent Cloud. Use the promo code 60PDCAST, that's 60PDCAST, to get an additional $60 of free Confluent Cloud usage. Be sure to activate it by December 31st, 2021, and use it within 90 days after activation. Any unused promo value after the expiration date is forfeit. And there are a limited number of codes available, so don't miss out. Anyway, as always, I hope this podcast was useful to you. If you want to discuss it or ask a question, you can always reach out to me on Twitter at @TLBerglund. That's TLBERGLUND. Or you can leave a comment on a YouTube video or reach out on Community Slack or on the community forum. There are sign-up links for those things in the show notes if you'd like to sign up. And while you're at it, please subscribe to our YouTube channel and to this podcast wherever fine podcasts are sold. And if you subscribe through Apple Podcasts, be sure to leave us a review there. That helps other people discover it, especially if it's a 5-star review, and we think that's a good thing. So, thanks for your support, and we'll see you next time.